Day 416 of doing a LeetCode problem every day until I get a job. All right, y'all, we're back again another day, another LeetCode problem where we're doing daily LeetCode problems. And today we have question number 2081, sum of k-mirror numbers. The difficulty level is hard, but don't worry because we're going to keep the solution as simple and easy to understand as possible. But before we get started, y'all, don't forget to like, comment, and subscribe. And if you need any new Apple AirPods, go ahead and check out that link in the description so you can get you some. Now let's see what the question says. A k-mirror number is a positive integer without leading zeros that reads the same both forward and backwards in base 10 as well as in base k. For example, 9 is a two-mirror number. The representation of 9 is in base 10 and base 2 are 9 and 1001 respectively, which read the same both forward and backwards. On contrary, 4 is not a two-mirror number. The representation of 4 and base 2 is 100, which does not read the same both forward and backwards. Given the base k and the number n, return the sum of n smallest k mirrored numbers. All right, y'all, so that sounds pretty confusing, I know, so let's go ahead and take a look at these examples just to make sure that we're doing this problem correctly. So in example 1, we're dealing with k equals 2, that means base 2. Now base 2, that's just binary code, but it's we have to remember it won't always be base 2. Like in example 2 it's base 3, in example 3 it's base 7. We'll handle those when we get there, but right now we're doing example 1, which k equals 2, which means we're doing base 2, and base 2 is similar to binary. So now that we know that, let's get into it. So in example 1, the input k equals 2, n equals 5, the output is 25. Explanation says the 5 smallest two mirror numbers and their representations in base 2 are listed as follows. Base 10 we have 1, base 2 is 1, base 10 3, base 2 would be 11, base 10 number 5, base 2 would be 101, base 10 7 would be 111 in base 2, and base 10 9 would be 1001 in base 2. And their sums, when we add them up, their base 10 sums, when we add up all of the base 10 numbers, their sum becomes 1 plus 3 plus 5 plus 7 plus 9, which gives us 25, and that's why our output is 25. Now, let's go ahead and break this down one step further just to make sure we have a complete understanding of what is going on. So first off, I'm going to give you an example of how we decode what the base 2 or the base numbers, right? So in this case, say we have 5, right? 5 is 5 in base 10 and 101 in binary or base 2. So base 2 just means we're only using 2 digits, 0 and 1. Those are the only digits we use, like binaries. Binaries only zeros and ones, so that's where base 2 comes from because it's only 2 digits, where base 3 will be 3 digits. Base 7 will have 7 digits, so on, so on. But in this case, we're dealing with base 2, so we're only dealing with zeros and ones, so, or i.e. binary. So 5 equals 101 in binary, right, or base 2. So let's break down how we got that, right? So say we take 101, say we have 101. That's our base 2 or our binary number, right? Then we come under here. So we're dealing with base 2. So when we're dealing with base 2, we take 2 from the leftmost, and we'll do it to the power of 2, right? So 2 to the power of 2. Then we come over here, and then to the next index or the next integer over, this would be 2 to the power of 1, right? Boom. Then we come over here, and this would be 2 to the power of 0. Let me get rid of these bases, clear this up for y'all. So this is how we get our binary code, right? So let me just, so it could look better for y'all and y'all could really better understand what's going on. So boom. So we have 101, and this is how we get 5, right, from 101. This is how 101 equals 5. So we do 2 to the second power will give us 4, and then so that we multiply that by 1. So it'd be 4 times 1 4 times 1. Then here, this would be 0 or 2 to the first power, which would give us 2 times 0. So it would be 2 times 0. Just so y'all know, this 1 comes from here. This 0 comes from here. This right here, this 4 comes from this right here. This 2 comes from this right here. And then over here, we do 2 to anything to the power 0 is going to give us 1. So it'd be 1 times 1, right? Boom. Then let's come underneath this with what those answers would be. So this would be 4 times 1 plus, we could say plus 2 times 0 will give us, so 4 times 1 equals 4. So it'd be 4 plus, then 2 times 0 equals 0. So it'd be 0. Then plus, we come right here, we say plus 1, because 1 times 1 equals 1. So when we do 4 plus 0 plus 1, that equals 5. Boom. So that's how we get 5 equals 101 in binary. That's how it works. We just going from 2 to the second power times 1. Then we do 2 to the second power times 0. Then 2 to the 0th power times 1, right? When we have the binary representation. But that's how it equals 5. That's how base 2 works, right? This is how base 2 works when we're dealing with only 2 integers, right? So now that we get that part, let's keep going through this. So we have the 5 smallest 2 mirror numbers. So we want the 5 smallest k mirror numbers. So in this case, so 1 is always going to read the same forward as backwards, right? So, or 1 number is always going to read the same forwards as backwards. So all of these base 10 numbers are automatically count as reading the same forward and backwards because it's only 1 digit. What we're really looking at now in this example is the base 2 example. So as you can see, base 2 examples, 1, once again, same forward as backwards, just 1. Then 3, same forward as back. 3 would be 1, 1 in binary or base 2. So 1, 1 is the same forwards as backwards. Similar with 5. 5 is 101. 101 is rated the same forwards as it is backwards. 7 is 111, which is read the same forwards backwards, and so is 9, right? So these are the first 5 numbers. Since n equals 5, these are the first 5 numbers where they have this principle where base 10 and base 2 both read the same forward and backwards. And it's only base 2 because in this case k is 2. Other examples, it might be base 3 or so on. So that's how we got it. Now say we look at 2. Say you see it goes from 1 to 3. It skips 2. 2 written in binary is 10, I believe. Yeah, 10 in binary. 2 is 1, 0 in binary. So that's why we skip 10 or skip 2. You see it's no 2 right here because 2 and base 2 would be 10. 10 is not read the same forwards and backwards. It's read forwards 1, 0, and backwards is read 0 and 1. So that's why we skip 2. Similarly to that, 4. Let's look at 4. 4 would equal 100 in binary. 100 binary or base 2. So once again, we skip 4 because 4 is not the same forwards as backwards, right? 4 in binary or base 2 reading forward is 100. But when we read 100 backwards in base 2, this would be base 2, it would be 001. So it's not the same forward and backwards. That's why we skip 4. Similar with 6 and 8. We just want the first 5 where it's read the same forward and backwards in base 10 and in base 2 in this example, or base k, whatever that may be. So in this case, these are the first 5 numbers because n equals 5. These are the first 5 numbers that read the same forward and backwards in base 10 and in base 2. So I hope that made sense to y'all, but just in case it didn't, let's go ahead and take a look at example 2 where they give us a different base number and n is a little bit higher. But now that we're dealing with base 3, let's go over how base 3 works. It works the same as base 2 like I showed you earlier. So with base 3, say we have a number 102, right? So 102 would be, 11 and base 10. 102 would be is the binary, right? So 102 is what it, or not binary, excuse me, base 3. So say we're looking at base, once again, so base 3 is going to work with numbers, have 3 numbers. So it's going to be 0, 1, and 3. I mean, excuse me, 0, 1, and 2. These are the base 3. These are the 3 base numbers. Remember, binary or base 2 only has 2 numbers, 0 and 1. Base 3 has 3 numbers, 0, 1, and 2, right? So that's how we're working with base 3. That's first what we need to understand. Now, let's show how we get 11 from 102, right? Base 3, 102, let's show how that equals 11 in base 10. So once again, it's similar to what we did in with base 2. So say we, let me just get this right for y'all so we could, so it can look better and you could understand better. So say we have 102, right? Boom. This time we're gonna start from the leftmost index. So we'll do 3 to the squared because it's base 3 this time. This time we'll do 3 squared. Then we'll do 3 to the first. Sorry, 3 to the first. Then we do 3 to the 0. Similar like we did with base 2, right? Let me just clean this up for y'all so it can be a little neater, easier to understand. Boom. So once again, similar like we did for base 2, we're doing the same thing for base 3. This time we're just using 3 instead of 2. So when we do 3 squared would be 3 times 3. Then we'll come over here. This would be 3 times 1. Come over here. This would be 3 to the 0. So this would just be 1, right? Boom. 3 to the 0 is 1. So boom. Then we come over here. We come down here. So it'd be 9 times 1. Boom. Then we come over here. It'd be 0 times 3. Sorry, y'all. 0 times 3. And then we come over here. And it would be 2 times 1. Boom. So then when we come underneath this, it's going to be 9 times 1. Boom. 9 times 1 is going to give us 9. Then we're going to do plus 0 times 3. That's going to give us 0. Then we're going to just come over here. We're going to say plus 2 times 1. Or excuse me, not 2 times 1. 1 times 1. Because this would be, oh no, sorry, yeah, it'll be 2 times 1. Because this 2 times this 1. 2 times 1. That's going to give us 2. Boom. Then when we add all these together, 9 plus 0 plus 2, that gives us 11. And that's how we got 11. That's how 11 equals 102 in base 3. This is how we got it. Boom. So now that we understand that part, well, I'll leave that there for y'all so while we go through the examples. So now let's look at example 2. In example 2, we have input k equals 3. That means base 3. Then we have n equals 7. So we want the first 7 numbers that are going to read the same forward and backwards in base 10 and in base 3. Then we want the sum of those numbers, which will be come out to be 499. Explanation says the 7 smallest 3 mirrored numbers are their representations in base 3 are listed as follows. So the base 10 was 1 in base 3, base 10 2, 2 is 2 also in base 3, base 10 4 is 11 in base 3, base 10 8 is 22 in base 3, base 10 121 is 11,111 in base 3, 151 and so on. Y'all get the picture. And when we add up all of those numbers, we get 499. This is how we got those base 3 numbers just using this principle over here, but we did it for all of these numbers, right? And these, once again, these are the first 7 numbers where they read the same forward and backwards. So for example, similar to before, say we had, you see it skips 3, right? So 3 and base 10, or excuse me, 3 and base 3 equals 10, right? And then similarly with 5, you see we skip 5 as well. 5 and base 3 equals 12. So as you can see, these numbers do not read the same forward and backwards. This reads 1, 0 forward and 0, 1 backwards. This reads 1, 2 forward and 2, 1 backwards, which is not the same, not the palindromic pattern that we're looking for, so we could skip these numbers. We want the first 7 numbers that read the same forward and backwards in both base 10 and base 3. So this is a better example because you see at base 10, we have this reads the same forward as backwards. Here it only stopped at 9, so you couldn't really see. But down here you can see it has to be read same forward and backwards in base 10 and in base 3. So once we, after 8 and base 10, we don't get another number that reads a K-mirror number all the way till we get to 121 and base 10, right? So that reads both forward and backwards in base 10 and base 3. So that's just an example of how it has to be in both base 10 and base 3. And yeah, as you can imagine, base 10 is just 10 numbers, which is 0 through 9, which is what we're used to. That's why it's base 10 is 0 through 9, whereas base 3 is 0 through 2, base 2 is 0 through 1. You get it? So now let's look at example 3. This time we're dealing with base 7, y'all. So once again, let's just go through how base 7 works, just in case it's still not making sense to everybody. So on base 7, it's the same principle. Say we are looking at number 101 in base 7, right? So 101 in base 7 is going to equal 203 in base 7. So 101 in base 10 is going to equal 203 base 7. Let me see this. This is base 10. Then we come over here, and we could say base 7 over here, right? So this is base 10. This is base 7 over here. They equal the same thing. Let's see how they got it. So once again, we have 203. Then we get rid of these periods for y'all. Come underneath that just so we can see how it works. So once again, start from the leftmost position. So it'll be 7 to the second. Then we come over here. Sorry, y'all. That'd be 7 to the second. Then we come over here. This would be 7 to the first. And then finally, over here, 7 to the 0. Boom. Let's just clean this up a little bit. Boom. Okay. Now, once again, same thing. So this time we're going to do, so 7 to the, this is 7 squared will give us 49. So we come right here. We're going to say 2 times 49. Because we take this 2 times this 2 times this 49. Then we come over here, it'd be 0. 7 to the first is going to be 7. So it'd be 0 times 7. Boom. Then one more over here. 7 to the 0 is always going to be 1. This is 3, so it's going to be 3 times 1. Oh, we could put a plus sign in here too, because that's what it's going to end up being. Boom. Then when we come over here, so 2 times 49, that's going to give us 98. Then it's going to be 98 plus 0 times 7 is going to give us 0. Then 98 plus, then 3 times 1 is going to give us 3. Boom. and that equals 101. 98 plus 0 plus 3 equals 101, and that's how 101 equals 203 in base 7. Remember, we're doing base 7 right now. This is how we got it. Then we multiply them and add those products together until we get this 101. So once again, that's how the base system works. Now, let's keep going with the example. I'm not going to go all the way through it, but as you can see, the output would be, what would this output be? It'd be 20,379,000, or not dollars, but 20,379. Boom. Explanation says, because n equals 7 this time, so we want the 17 smallest 7 mirror numbers are 1, 2, 4, 5, 6, 8, 121, 171, 242, so on, so on. Once you add up all of these numbers together, this is what you get, 20,379,000. And that's how we got it, y'all. So we want to do that for all of, or whatever they throw our way. K will not always be the same, so it might not always be base 2, might not always be base 3, we might not always be base 7, but we want to be able to write code that handles whatever base that they give us. We'll be able to find the first n k mirror numbers. So I hope that made sense to y'all. And now that we understand the question, let's get into the fun part, the actual solution. I know that was a lot to take in, y'all, but bear with me, stay with me, y'all. We're still going, we're just getting started. Now, the first thing we are going to do is we're going to create a helper function. So we're going to come outside this main function. We're going to create 2 helper functions, actually. Now, this first helper function is going to check if a number is a palindrome in base K. So for that, we can say func check base K, open up the parentheses, we're going to say underscore num colon int. Then we're going to say comma underscore K colon. That's going to be an integer as well, and it's going to return, sorry y'all, it's going to return a Boolean. Boom. Now we need to convert the number to a string representation in base K. So we're going to say declare a variable called str, set that equal to an array, open up the parentheses, we're going to say string, open up parentheses again, we're going to say num, comma, radix, colon, K, just like that. Now we need a 2-pointer approach to check palindrome properties. So we'll come underneath this and we'll say var s, set that equal to 0. Then we'll say var e, we'll set that equal to, or we could change it, or whatever. Then we'll say var e str.count minus 1. Then we're going to come underneath this, we're going to say while s is less than or equal to e, boom, we're going to check for our palindrome. So we're going to say if str square bracket s does not equal str square bracket e, we're going to open up the brackets and we're just going to return false, just like that. Then we're going to increment s and decrement e. So we're going to come over here, we're going to, under here, we're going to say s plus equals 1. Then we're going to say e, sorry y'all, e minus equals 1. Boom. Then we come outside of this while loop and we could just say return true, if meaning we found a palindrome. Boom. Now that's the first helper function, but we still need another helper function. So we could come above this function really, but still outside the main function. It doesn't matter. Come below this function, above this function, doesn't really matter. So this second function, this is going to be a helper function as well to generate the palindrome in base 10. So when we create this, D is going to be the length of half of the palindrome for odd palindromes and middle digits included. Odd and even arrays are going to be updated with palindromes of the current length. So for this, we could call this function func gen base 10. We're going to open up the parentheses. We're going to say underscore D colon, that's going to be integer, comma. Then we're going to say underscore odd, colon, that's going to be in out, and that's going to be an array of integers. Come outside of that array of integers, we're going to say comma. Then we're going to do the same thing for even, colon, that's going to be in out. That's also going to be an array of integers as well. Boom. Now we can open up the brackets. We're going to say if D if D equals 1, our base case, the single-digit odd palindrome and two-digit even palindrome. So we're going to say, we're going to open up our brackets, and we're going to say odd equals, we're going to open up the parentheses, and we're going to create an array of integers 1 through 9. So we're going to say 1, 2, 3, 4, 5, 6, 7, 8, 9. Boom. Now we're going to do the even are going to be the double-digit representations, basically, kind of. You'll see what I mean. We're going to say even equals, this time we're going to say, instead of just 1, 1, we're going to say 11, right, for 2 ones. Then same thing, we're going to do 22, comma, then we're going to do 33, comma, then 44, comma, then 55, comma, then 66, comma, 77, comma, 88, comma, all the way up to 99, comma. Boom. Then we can come right here, and we're going to say else. Then we're going to open up the brackets. Now we need a new list of odd length palindromes for the current D. So we're going to say var new odd. We're going to set that equal to an array of integers. Put the parentheses outside. Same thing for even. We're going to say var new even. That's going to be an array of integers as well. Put the parentheses should come outside of that, like that. Boom. Now we need powers of 10 for splitting and combining parts of palindromes. So we're going to say let 10 half. That's going to equal an int. Open up the parentheses. We're going to say pal. Open up parentheses again. 10.0, comma, double. Open up the parentheses. D minus 1. Just like that. Then we're going to say let 10D, that's going to equal, and open up the parentheses, pal, open up the parentheses, 10.0, comma, double, open up the parentheses, D. Boom, just like that. Then we're going to come underneath that. We're going to say let 10D1, that's going to equal integers again, open up the parentheses, pal, open up the parentheses, 10.0, comma, double, open up the parentheses, this time it's going to be D plus 1. Boom. Now we need to build new odd and even palindromes based on previous even palindromes. So we're going to come underneath this. I'm going to say for num and even, we're going to open up the brackets. We're going to say for I and 0, ... 9. We're going to open up the brackets, and we're going to construct a new odd palindrome by inserting digit I in the middle. So we're going to say let temp odd equal num divided by 10 half times 10 half times 10D plus I times, or let me just do it like this so you can read it easier, because remember we got a PEMDAS, just how PEMDAS works. So we're going to say I times 10 half. Then we come underneath that, and we can say plus num mod 10 half. Then we're going to say new odd dot append, open up the parentheses, temp odd. Just like that. Now we need to construct a new even palindrome by inserting the digit I into the middle position. So we got to do the same thing for even. So for that, we're going to come under this. We're going to say let temp even equal num divided by 10 half times 10, this time times 10 d1. Then we come underneath that, we'll say plus I times 10d. Come underneath that, and we'll say plus I times 10 half. Then we'll come underneath that, and we're going to say plus num mod 10 half. Boom. And then we're going to say new even dot append, open up the parentheses, temp even. Just like that. Now we need to update the reference arrays to the newly generated palindrome. So we could come right here outside of the for loop, and we're going to say odd equals new odd, and we're going to say even equals new even. Just like that. Now we're not done yet, y'all, but we're done with the helper functions. These are the two helper functions. Now it's time to get into, excuse me, y'all. Now it's time to get into the main function, right? So for this, we need the current length of half part of the palindrome generation. So we're going to say declare a variable called d and set that equal to 1. Then we need the number of k-mirror numbers left to find. So we're going to say declare a variable called n. We're going to set that equal to n. Then we need the sum accumulator for the k-mirror numbers found. So we can start, say sum equals 0 to start. Then we need the list to hold the generated odd length palindromes and even. We need odd and even, so we're going to declare a variable called odd. That's going to equal an array of integers, put the parentheses, then we do the same thing even. That's going to equal an array of integers and put the parentheses. Boom. Now, let's get into it. Now we need to repeat this, or we're going to use a while loop until we find k-mirror numbers. So come down here, we're going to say while n is greater than 0. We're going to open up the brackets. We're going to say gen base 10. Then we're going to open up the parentheses. We're going to pass in d, and it's in and out, so we put this and before odd. And same with even, we got to put the and before even as well. Boom. Now we need to combine the odd and even palindromes generated at this length. So we come underneath this, and we can say let base 10 equal odd plus even. Boom. Now we need to check each palindrome if it's also a palindrome in base k. So for that, come underneath this, we can say for num in base 10, we can open up the brackets, and this time we're going to call if check base k, open up the parentheses, we're going to pass in num and k, come outside of that, open up the brackets, we're going to say sum, we're going to add the k-mirror number to the sum, so we're going to say sum plus equals num. Come underneath that, we're going to decrement the count of how many more that we need to find, so we're going to say n minus equals 1. Then if we found all required, then we could just return the sum. So we could say if n equals 0, we could open up the brackets and we could just return sum. Boom. Now we need to increase the palindrome half length and repeat. So for that, we come right here and we say d plus equals 1, And finally, we need to return the sum after finding all nk mirrored numbers by coming underneath this and saying return sum. Now that should be all she wrote, y'all. Let's give that a run. I know that was a lot. That was a lot today, but we made it. We got through it. We got an error already. Let's see. This should be an equal right here. It's not that big of an error. We can handle that little error. Boom. Let's run it again. Let's see. Okay. Where we at? Okay. So this should be shouldn't be a space right there. Let's run it again. Let's run it. Okay. Now where we at? Oh, this should be minus equals. Let's run it again. Let's see, it's a lot of code. Ooh, and it's accepted, y'all. So let's go ahead and submit it. Make sure it's still accepted after we submit it. Let's see, and look at that, y'all. That's what I'm talking about. 897 milliseconds beats 100% of users. Those are some good numbers right there. Those are the numbers I like to see. So before we leave, y'all, make sure you get one more look at the code. This right here is the first helper function. Boom, read it, learn it, love it. This is the second, or this is the top half of the second helper function. This is the top part. And then this is the bottom part of the second helper function. Boom. And then this is the top part of the main function. Boom. This is the bottom part of the main function. And yeah, y'all, with that being said, I hope y'all learned something today. And I hope to see y'all here tomorrow for another day, another LeetCode problem. See y'all then.